Um, so I'm Dino Jaroszynski, as Antoine has kindly introduced me, and I'm going to be talking about radioisotopes. So let me just share my screen so I can start my talk. And like many projects in physics, in science in general, maybe, it always involves collaboration. And in physics, it quite often involves a lot of equipment. And in particular, in this case, the usage of a high power laser. So that's how it fits into Laser Lab Europe. So what I'm going to talk today about is how do you produce radioisotopes using a laser-driven accelerator. Now, accelerators are normally very large, and the whole idea here is, can we make the whole facility applying an accelerator much, much more compact, because you can reduce the shielding and all the equipment associated with accelerators. So I'm at University of Strathclyde, as Antoine has introduced me, and this University of Strathclyde is in the central belt of Scotland, and it's part of the Scottish University Physics Alliance, which is a collection of university which we have a doctoral training school associated with that. What I'm going to talk about now is now becoming part of the EUPOPA project, which is a project that actually Antoine leads to produce radioisotopes. And we've done some work prior to the start of this project, and we're still analyzing the data, so it becomes part of EUPOPA. But this project is funded by the Department of Energy Security and Net Zero, and involves several collaborators. So these collaborators are from National Physics Laboratory, Giuseppe Lurosso and Dave O'Donnell from the University of West of Scotland, and the UKEA, and we've had people participate in experiments from UCLA, Silvia Chipiccia, and Jose Hernandez from CLPU. And we use the facility SCAPA, which Antoine mentioned. And there are several people, they're all physicists, even though we run a laser. Everybody who runs a laser basically are physicists, plasma physicists, in fact. So they all participate in experiments. So what I'm going to talk about today is the production of these transmutation of material into radioisotopes, which can be used for therapy, for radiotherapy and for imaging. And the methods we use to do that is using this accelerator, very compact accelerator, only a few millimeters long, to produce bremsstrahlung radiation in a heavy target, and that's used to transmute. In this case, we transmute zinc into copper. We also transmuting nickel as a sort of test standard for the measurements. And we use our resources are a facility, the laser facility, and beam lines, which is this operating environment. And the last bit of it, actually, which is quite important, is how do we scale? So we've got some very good results, but how do we scale that to an operational commercial production system to produce at least 1 gigabecquerel amounts of radioisotope activity, and the proposal here is by increasing the current produced by these accelerators. So you'll see my suggestions towards the end of the talk. So a little bit of background is that, as Antoine said, we set up the Alpha-X project, and one of the main results of it, this was a project led by Strathclyde, was one of the Dream Beam papers, first demonstrating the laser Wakefield accelerator in 2004. And we also have investigated the plasma photonics aspect, is how can you use plasma as a means of controlling light. Amplification of light is one of the applications of this. And also a very important part of it, and which includes industry as well, is the application of secondary sources. So this is really a big focus of my activities. Some of it is, for example, producing a beam, producing a free electron laser, which was proposed in 2002. We never succeeded in doing that because we never got money to build the actual beam line. But this has now been demonstrated by other facilities around the world, even though we were first to propose it in 2002, which is a little bit unfortunate for us. But we're developing new systems that can replace the free electron laser, for example, the ion channel laser, and using plasma undulators to produce hard X-rays. So in a sense, to do some of the work of synchrotrons for sort of a niche application for synchrotrons. But one of the important outcomes of our studies is also producing attosecond electron bunches, which can be used directly to produce coherent synchrotron radiation. So we have already demonstrated producing coherent radiation from an electron beam in an undulator. And finally, we have a big theoretical activity looking at collective radiation matter interactions, high field physics, for example, radiation reaction, and laser beam propagation in atmosphere, for example. So the objectives of this project called MRIP, this innovation program, medical radioisotope innovation program. Our title of our project is called MedRadLasers. It's this collaboration with NPL and the University of West of Scotland. So the idea there was to demonstrate the laser Wakefield accelerator driven by a titanium sapphire laser to produce gamma rays by bremsstrahlung, and to induce photonuclear reactions to produce medical isotopes. And the purpose of that was to demonstrate the scaling of that for a commercial system ultimately. And so we chose to transmute zinc into copper. So we use both natural zinc and pure zinc 68 to transmute into copper 67. And we quantified the yield, and we also investigated the contaminants such as copper 64 and copper 66. Now, the interesting thing about copper 67, it's a beta emitter, and it's an emerging isotope, radioisotope for cancer treatment. And also it can be used in combination with other isotopes like copper 64, which are chemically similar, and you can use them as a theranostic pair of isotopes to do simultaneous imaging and PET imaging or SPECT imaging simultaneously with a beta emitter like copper 67. So you can then target the tumor while observing where the radioisotope is going to. Right. Okay. So let's quickly summarize, or I'll quickly review what a Wakefield accelerator is. A lot of you may already know. But an intense laser beam is focused into gas. It makes plasma. So you're always talking about plasma physics. So this intense laser beam is intense enough that electrons become relativistic in the electric field of the laser beam. So you're talking about densities of 10 to the 19, 10 to the 18 electrons per cubic centimeter, and intensities that are multi-terawatt powers and intensities above 10 to the 18 watts per square centimeter. And the idea there is to drive the plasma into what we call the nonlinear regime, the bubble regime, which produces linear fields. So it sounds like a bit of a contradiction, but actually by excluding all the electrons from a region, trailing a high intensity laser pulse traveling almost at the speed of light, one has very linear fields, and these can actually produce very high quality beams. And also by controlling the density and the density profiles and so on, one can inject a lot of charge into these structures. Now, these structures compared with a conventional accelerator, you're talking about tens of microns compared with tens of centimeters for a conventional accelerator. So they're very, very compact. So the whole accelerator is only a few millimeters long, okay, certainly for the applications that I'm discussing at the moment. And all you do, which is amazing, you just focus the light into gas, and out come these electrons, because the relativistic effects or the relativistic changes of the dielectric properties of the plasma, the optical properties of the plasma, cause the laser pulse to self-focus. So it ends up self-guiding. And that means that you can produce a stable accelerator, and you'll see this is already starting to work almost like a conventional accelerator. Okay, so we've demonstrated that. And you can also, it's a very versatile accelerator because you can tune the energy, the final energy of the accelerator, just by changing the density of the gas or the plasma, okay? Or you can change the wavelength. So you see here, I've got an example of a 10 micron laser, and you're here right at the other end. I'm just showing it here just to alert you to the fact that, hang on, I have to go back. I don't know why that slide only stays on for a short time. I haven't been able to solve that. Anyway, but going to longer wavelengths, one has a larger ponderomotive force, and actually you get a much more effective accelerator and much more compact accelerator. So that's why I introduced this. And also the densities are lower, so everything becomes much easier. Anyway, the requirement here is you must be above the critical density for self-focusing, and you get acceleration. So the facility that we did the work at is SCAPA. It's the Scottish Centre for the Application of Plasma-Based Accelerator. It's the largest university-based laser in the UK, and certainly the highest repetition rate one in the UK at the moment, or, per se. Sort of these are petawatt scale lasers, sort of hundreds of terawatts, depending on how you define it. Anyway, this is a 5 Hertz accelerator, 350 terawatts, titanium sapphire. And the experiments are done in one of 3 bunkers. In this case, we chose bunker A. We have this beam lines in bunker A, where we can accelerate particles and produce radiation, electromagnetic radiation. So what does it all look like? Well, the accelerator is very unremarkable. It's just a nozzle, a gas nozzle, and you pressurize the nozzle of the pulse valve, and you produce a column of supersonic column of gas, and that's ionized by the laser beam, and that's only a few millimeters long. Okay, and then you for these experiments we assembled a whole lot of equipment, which you'll see in a further slide. But the target chamber is very simple. It's just basically many optics for setting up, essentially. But the accelerator itself is very, very compact. And outside the regions of the electron beam is taken outside of this vacuum chamber where the accelerator is. And that then is passed through things like a spectrometer, or is allowed to go straight forward to measure its energy. Straightforward to irradiate material to produce radioisotope. So it's similar to conventional accelerator laboratories, just quite a bit more compact. Okay, so the parameters are here. I won't go through them, but we have 2 lasers. The one we use on the right-hand side, and actually it seems to be quite a good accelerator. A good laser, and so the pointing stability, actually that's wrong, that I've got there. It's about 5 or 10 microradian pointing stability. Energy stability of the laser less than 1%. It has a small divergence, this is the electron beam. The electron beams can have energy spreads between 1 and a few percent, and charges up to a couple of hundred picocoulomb. And we can use different types of media, gas jets, gas cells, capillaries, and so on. And we can produce energy in the range of, in our lab, we've demonstrated 200 MeV to about 5 MeV to about 1 GeV. And we participate in other experiments, for example, in Texas, where we demonstrated 11 GeV. And we're looking at different accelerator mechanisms, injection mechanisms. So copper-67. So that's an interesting isotope. So if we can produce gamma rays, we can transmute zinc into copper, and in particular copper-67. And this can be used for diagnosis of tumors and also for treatment of tumors simultaneously. And it has a chemistry that allows it to be combined with ligands to take it to the tumor, and it has a lifetime of about 60 hours or so. So it's an excellent for SPECT diagnostics, and also emits a beta particle emitter, and it's the half-life. And I'm not a physician, but the half-life is comparable with the lifetime of antibodies in the tumor. And it can be used in conjunction with another isotope, copper-64, for PET imaging. So you can essentially do PET imaging simultaneously with treatment. So that's why it's really interesting. All right, so of course you can produce a range of copper isotopes, and they all have different lifetimes, from several hours, from several minutes to several hours. And in our case, we've chosen copper 67 by transmuting zinc 68 into copper 67. So the basic setup of the system is just, it's very, very simple. In fact, this simulation of the setup, it's just a converter to convert the electron beam energy into bremsstrahlung energy, and the spectrum of bremsstrahlung radiation varies from more or less the electron energy down to very low energies. And by designing the target and the converter, one can then optimize the overlap between. So you put the copper, for example, in our case, we also use zinc. Zinc into this aluminium cylinder. We can also put in nickel, because we use nickel as a standard, so as to compare with a well understood isotope production, which has a well understood cross section. And we designed this. So Barish Bingel has done a lot of the design. He's a PhD student working on this project, and we've come to a very good design. And the spectra that you can use, in fact, it's quite interesting. This is a 2 millimeter thick tungsten converter in front of the target. And by varying between 50 MeV and in this case, I show 100 MeV, but we've done measurements up to 200 MeV. You produce photons, significant number of photons. These are numbers of photons per centimeter squared per primary electron. So if you have, let's say, 150 picocoulomb, you're talking about sort of 10 to the 9 electrons of that order. So you're producing similar 10 to the 10 photons. So the idea is to the yellow region there is where the photon energy range, where you get a significant production of radioisotopes. And the reason why I show this as well is that actually it's quite important to choose the energy of the electron beam, because if you have too high energy, you can produce contaminants. And you'll see in our experiments, we were able to show that using a 50 MeV beam, we can then produce radioisotopes with a low concentration of contaminants. Okay, so the measurements, the way, once you've irradiated the zinc in this particular case, you produce the isotopes, and the isotopes emit 511 pairs of photons and some line emission. For example, zinc 68 will produce 185 keV photons when you produce copper 67, and you'll get a small amount of 511 from this particular measurement. So you can then use, by identifying these lines, you can then calculate the activity that you produce. And you can see here, the lower plot there shows the experiments where we use natural nickel as a target, as a standard target. We want to make sure that our measurement system is good. And you'll see now that we have some discrepancy between the predicted amount of activity and the measured activity. In fact, we measure much more activity than is predicted. But so that's still an unanswered question. But one important aspect of this project is that we need to know the charge of the electron beam coming in. So what we've done is we've measured the the calibrated charge when the electron beam passes through a fluorescent screen, LANX. We use LANX in this particular case, and then the electron beam. So that allows us to, on a shot-to-shot basis, integrate the signal, the image. You'll see in the later slide an example of that. but we also have used calcium chloride, where we produce 511 photons, and we can we can directly measure the photons. So so in this particular case, we have we measure the gamma rays from calcium chloride. There's a mistake there, and we measure that as an online monitor. And the calcium 39 and calcium 37 have lifetimes of around 0.8 seconds to 0.1 seconds, so they radiate many, many photons in a short time, within of the order of 1 second, and that means we have a very good signal. In fact, we have too many photons, so our detection system did saturate from time to time. And in this aluminium container, we produce enriched 95% enriched zinc. In zinc 68 as a target. We also use natural zinc, and the nickel is the natural nickel that we use for the for the standard measurement. So the activity is measured using a high purity germanium detector, which is surrounded by shielding to reduce the background to a few percent. And these signals are then detected in multi-channel analyzer, and allows time stamping of every event and allow the time evolution to be detected, and therefore the lifetime of the particular lines that we measure, and that allows us to identify the particular isotopes. And we've done the experiments have been carried out with 2 energies, 50 MeV and 200 MeV, and we've used 4 targets: natural zinc, natural nickel, low density, natural nickel, high density compacted, natural zinc, low density. We also wanted to understand in terms of the target construction, the effect of working at low densities and high densities. And nickel target has been chosen as a reference because it has a well-known photonuclear cross-section. And repeated irradiation runs allowed us to check repeatability, so we're quite sure about our results. And you'll see from the tables I'll show later. So anyway, so nickel reference is quite interesting because, as I said, it's has a well-known cross-section, and we can just directly measure the activity of nickel. So an important part of the project has been to properly irradiate the target, and it turns out that our accelerator is very stable, and you'll see in the later ones, but also not only in terms of number of electrons per shot, but also the energy distribution and also the pointing of the electron beam. So you produce a beam which is about 1 or 2 milliradians in divergence, slightly elliptical because of betatron oscillations of electrons in the accelerator itself, and the pointing varies by the order of 1 or 2 milliradians, and you can see that plot that I've showed there. The dotted line indicates where the target is, the projection of the target onto the Lanx screen, and those points there, the distribution are the centroids of each pulse that's incident on the Lanx screen, and an example single shot of an Lanx screen is on the left-hand side. So from that, we are able to then actually get quite a good result. So this is, well, obviously I've chosen the best one. The worst ones are only about 30% worse than that, slightly asymmetric, some of them. But we produce between 100 and 200 picocoulombs per pulse at 50 or 200 MeV, slightly elliptical. And the interesting point of this is that some of the electrons and some of the gamma rays will fall outside the region where the target is placed. So that means that not all the gamma rays will then be incident on the target. So one has to take that into account when you calculate the activities, or try to determine whether the activities are reasonable. So this work didn't just start with the the current project that I'm telling you about. We actually, some years before, we did some experiments with natural zinc, and we looked at producing transmuting zinc 64 and producing copper 62. And that was just basically a test of our capabilities at that time. So, and the data is not very good at that time. It's improved hugely since then. But this just shows you that we were able to measure the activities. We were able to show that we produce some tens of kilobecquerels of activity. So this is quite important for the community. We were able to also demonstrate that we can monitor the gamma rays on a shot-to-shot basis using this calcium chloride monitor. And this just shows you the charge that we measure looking at the Lanix screen. So each one of those images down below was integrated. And over a long period of time, we were able to irradiate for 5 or 6 hours continuously at 1 hertz. So it's quite remarkable. And we're then able to, the plots below that you see, those lines, those curves there, are the monitor that we use, the calcium chloride monitor, where we just measure the radiation coming from that using this gamma ray detector. And and in this particular case, this is a good example of running from 1 o'clock in the afternoon until about half past 4 with very, very few breaks. You can see there's some gaps where the camera for the Lanix observation screen didn't work. We were able to then to use that data to interpolate missing data, which is quite good. So we can get quite a reliable measurement of the average current or and to determine the total dose expected. And so we measured the gamma flux using 2 different types of detectors. And we also did this experiment with nickel. So both with natural zinc and nickel, and also with purified zinc 68. So the main results that we had for different targets and different isotopes, we were able to have about 23,000, I think, around between 10 and 20,000 shots, and we were able to produce about 10 kilobecquerel of zinc of copper 67 in these targets. So this is with 200 MeV beams and with 50 MeV beams. So that shows you also that with 50 MeV beams, even though the average charge per shot is very similar, we produce less photons because of the small difference in the energy. That's not very significant. So we produced activities between 9.3 and 7.5, so very little. And the only puzzling thing about it is that using our simulations, we predicted about 1.5 kilobecquerels for these particular runs, or even 0.5 kilobecquerel. So there's an unknown there, and we got some ideas about why there's this large difference. But so the main results, this is just basically a table of our main results. It shows that we produced in nickel, for example, we produced about 15 or so kilobecquerel, and with zinc, we produced about 10, 5 and 10 kilobecquerel. And we were able to then to calculate the activity per picocoulomb and the activity per shot, per laser shot, for example, and the total. So we were able to actually get quite a lot of information. So the number of shots in these particular cases, so some of them we even had hundreds of thousands of shots, so 234,000 shots You can see here for the production of the enriched zinc, copper from enriched zinc, we did experiments of 18,000 shots. So in that particular run, we didn't have as many shots. So it's just the normal misfortune of setting things up on a particular day. So that's what I call fate. Anyway, so one of the main results that come out of this, and Antoine or somebody, can you just tell me, because I don't have a clock in front of me, tell me when I'm sort of getting towards the end of my talk. But the main results of a summary of isotopes detected, or one of the main results is not just the activity and therefore the number of atoms, but actually what contaminants did we produce. So that's really, really interesting because, of course, contaminants are generally unwanted in these applications of the isotopes for therapy or for imaging, because they can be toxic to the body. And we've been able to show that choosing 50 MeV electron beam energy, the amount of contaminants in terms of percentage of atoms is down less than 1% or that order. And so that's an interesting point, still work in progress, but so an important part of what we do, or what we've done, is how can you produce, because a single patient dose of copper-67 would be a 1 gigabecquerel. So we produce 10 kilobecquerel. So how could we, the question is, can we produce the amount of activity you need for one patient dose? So the answer to that question is using our laser running at 1 hertz. No, even if we run 24 hours a day, continuous operation, we can only really produce about 200 megabecquerels. Oh, sorry, 200 kilobecquerels, because of the fact that the lifetime is about 62 hours, and continuous operation is sort of saturates because the activity decays away as you are producing the isotopes. And if you have a shift 9 a.m. to 5 p.m., you can produce an activity of 50 or 60 kilobecquerel. So, and this doesn't, you could inject more charge, and I'll show you later that we have a method of doing that. So we could bump up the charge, and you'll see right at the end, I'll show you some scalings. Okay, so how do we optimize this? So current production that we've demonstrated is 10 kilobecquerels in 5 hours. We can inject more charge. Okay, we can go to 1 nanocoulomb per shot per pulse, which is 1 nanoamp for 1 hertz. And using this bump injection, which I'll tell you a little bit about in a minute, we can, using a particular type of gas jet, we can increase the activity by about 7 times. So we can produce, in 5 hours, you can produce 67 kilobecquerels. We could run SCAPA at 5 hertz because it's actually designed to run at 5 hertz. But generally, we're nervous about doing that because you don't want to destroy our laser. And it would increase the activity by a factor of 5. So we can go to about 1/3 of a megabecquerel in 5 hours. We can optimize the target. So in other words, we can work more on optimizing the target size and length and so on. We can increase the activity by a factor of 2 or 3, so we can get about 1 megabecquerel in 5 hours. We can run continuously in 24 hours, and so we can go to about 20 to 30 megabecquerels. So this is suitable for animal studies. And to reach 1 gigabecquerel, which is single done, we're using titanium sapphire lasers, we'd have to operate at 100 hertz, which is very challenging. And with this particular case, steady state activities would be 10 gigabecquerels. Okay, or we can use some new laser technology. Optically pumped CO2 lasers would give 160 times larger point of motive force, and it's much more efficient than current technology for laser Wakefield accelerators. So how do we control the charge injected? Well, we can vary the plasma density very briefly and a small region in the plasma, and by controlling the size of the bump and the length of the bump, we can either go to produce very short bunches, so we produce In fact, we've done this in the lab. We produced 260 attosecond. We've actually got shorter than that in the lab. But you can go the other way. You can increase the bump size and the length and so on. And so you can then, the top line, the dotted line is which line? Let me check which one is which in this particular case. So 3D is a square. The top line is the 3D simulations. So it shows that by changing the bump parameters, you can go up to about 300 picocoulomb. So we extrapolate that to about 1 nanocoulomb. So that's one way of doing it. And the other one is to go to longer wavelengths, to go to 10.6 microns using CO2 technology. So we've done a simulation study, and we've been able to show if you go to longer wavelengths, you go between 1 micron, 800 nanometers and 10 microns, you can then start to produce, even at 6 microns, if you can get a 6 micron laser, you're producing 12 nanocoulomb per pulse. And this is using, I think this used a 5 joule laser of that order. Anyway, but it means that you can also, we got longer wavelengths, you get lower energy, and we can produce about 100 MeV with energies of charges of about 12 nanocoulombs. And if you want to go to very higher pulse energy per pulse, let's say 100 or 400 joules per pulse, then you can produce very high energy and very, very high charge. So you can start approaching a microcoulomb with these particular cases. So I'm pretty confident that if you built something like this, you could then optimize it to produce, even at low energies, you get charges of the order of microcoulomb per pulse. And that makes things actually quite interesting. So, and then if you think about it, it all depends on the average current, okay? If you assume a 50 MeV beam, then the average current translates into increased activity. Okay, so this table shows you're running at 1 hertz. So at 5 hertz, you get 5 times more average, higher card. 100 hertz, higher average current. 100 hertz, you go up by a factor of 100. So, and if you run it at 1 kilohertz, you can be up by a factor of 1,000. So that means that you can go from 0.15 nanoamps to 150 nanoamps. And if you and this is still a challenge, if you produce 1 nanocoulomb per pulse per bunch, you can go from 1 nanoamp at 1 hertz, similar to what we are doing at the moment. Well, similar laser to what we have at the moment, and by going up to 1 kilohertz, you're producing 1 microamp. So that's a 50 watt in the actual beam. So, but however, if you produce, if you go to longer wavelengths, 10 micron laser wavelengths, then you can produce about 150. So I've been very realistic about the charge. Okay, I think we can probably get up to a microcoulomb, but let's say 150 nanocoulomb. So immediately, if you go from 150 picocoulomb to 150 nanocoulomb, you got a factor of 1,000 increase just by changing the laser. So you can then produce 150 nanoamps. So it's similar to running a 1 kilohertz laser. It's a titanium sapphire laser. But if you go up to kilohertz for a CO2 laser, then you can produce 150 microamp average current. And so the average beam power is about 7 kilowatts. So you're starting to have to worry about the targets and the converters when you get up to those, because there's a significant amount of power in the beam. Okay, but so the bottom line, this is my sort of penultimate slide, I think. So this shows you here where we are. So on the left-hand side is what we've done. And on the we've been able to show the black line is 5-hour irradiation. That corresponds to our experiments. So that produces about 10 kilobecquerel. If you go to 5 hertz with our laser, 150 nanocoulomb pulses. Anyway, but the bottom line for this is that I've drawn up the 1 gigabecquerel single dose. So titanium sapphire running at 100 hertz or kilohertz, you should be able to get single dose amounts. Okay, But if you go to CO2 technologies, you can actually produce the isotopes that are necessary, that are useful for a hospital or even for a whole country. So it's worthwhile, investigating that type of technology. So I think that's really the bottom line of what I'm saying. There are other methods, by the way, of getting a lot of more charge, and that is by using a self-phase modulation, laser acceleration, in that way you can increase the charge. But these lasers tend to be very big lasers producing 100 joules or something like that of laser energy. So it's quite challenging to get these to run at high repetition rates. But these are other lines of research. And so in conclusion, and maybe I should mention why one uses the photonuclear reactions rather than using a protons to transmute the atoms into the radioisotope, the nuclei into radioisotope nuclei. And that is because you have another control of the contaminants, and you can also make theranostic pairs. It's very compact. You're talking about millimeter cubed to centimeter cubed accelerators, and we think that this will advance the science of these radioisotope application of the radioisotope. And for the UK perspective, I should really put EU there, by the way, but increase the EU capabilities by having this type of a resource. And uniqueness, compactness, ultra tunable, and you can lead to discovery, may produce other types of radioisotopes, and CO2 laser technology could make it feasible to increase the yield to practical levels. And just to show off our facility, we have a unique university-based laser facility called SCAPA, great laser, great facility, and we have a lot of new opportunities where we could establish a niche production. And this is a disruptive and transformative technology, I think, and it's relevant to society. So that's basically all that I have to say. So thank you very much.